All right, in this video, we're going to look at another application of polynomials, and that would be maximizing area. So again, this is, by the way, this is number 5 from your homework packet. So guess what? Put away your notes, get out your homework packet. This way you'll have all the numbers and everything in front of you, so you don't have to worry about trying to jot all this down. The only issue, you might not have enough space. Hopefully you have enough space, but personally, I write rather large, and so so you might need to do this on a scratch paper off to the side, or maybe even in your notebook. So maybe just in your notes, say, look at number 5 from your homework assignment for this problem. All right, so let's get started. So it says a rancher has 300 yards of fencing materials and wants to use it to enclose a rectangular region. What dimensions would give a region the maximum area? All right, so I'm a visual person, so let's draw a diagram to help us out. So here we have a rancher that's got 300 yards of fencing material. Well, if you think back to your geometry days, that 300 yards of fencing material is referring to your perimeter. Well, remember, we have length and width. So, whoops. So we have length and width here. So the equation that we would have for our perimeter would be, well, we have, if we were to add all these sides together, we would have L plus W plus W, or a much better way to write this would be 2L plus 2W. So that's our equation for the perimeter. But we're trying to maximize the area. So the area, remember, is length times width. So in order to answer this question, we're going to use the perimeter, and we're actually going to have to use both these equations to figure out what the dimensions would be. And then once we have the dimensions, then we can multiply those dimensions together to maximize the area. All right, so let's think about what we have there. So the 300 yards of fencing material, obviously that represents your perimeter, like we just mentioned. And so we're going to use this equation where P is the 300. So I actually have that on the next slide. So like I said, I don't have enough space here to do all this. So I'm going to go to a new slide here. So this would be your equation for the perimeter. So we'd say 300 equals 2 times the length plus 2 times the W. Now you can solve for either dimension. It does not matter which one you do. So if you're wondering, why did you do L? Why didn't you solve for W instead? Well, I just chose to solve for L, meaning I'm going to get this equation rewritten so the L is by itself. So I'm going to subtract 2W from both sides. And then I'm going to divide everything by 2. So we would have, I'm going to write it like this. L equals 300 minus 2W, but we're going to divide everything by 2. So when we do that, 300, if you notice, this can all be reduced, or everything divided by 2 would end up being 150 minus W. So that's our equation to find the length. So the length is equivalent to 150 minus W. How does that help me? Well, remember, area, actually let me do a different color here. Area is length times width. Okay, we had that on the previous slide. So what we just did is we said that L is the same as 150 minus W. So we would have length times width. So 150 minus W times the width. Well, to simplify this, I'm going to distribute the W through. Or if you want to think of it this way, in standard form, it would be negative W squared plus 150W. Okay, so how does that help me? Well, if you think about it, we have a quadratic. And if we were to just sketch a graph of what this quadratic would look like, I'm going to do that over here. So this would be a parabola opening downwards, because again, it's a negative W squared. So we want to maximize. So let's say if we had our x-axis. So the way this is set up, my equation that we have over here in yellow, L equals 150 minus W. The W would be your independent variable, like your x, and the L would be your y. So I'm going to call the x-axis the width and the y-axis the length. So what we want to do is we want to figure out the maximum dimensions. And so the maximum dimensions would be the vertex. So we would have this point and this point. So this would be your h value in your vertex, and this would be the k value in your vertex. So to find out what h is, we're going to do the opposite of b over 2a. So opposite of negative 150, or opposite of 150 would be negative 150 over 2a. Well, a is negative 1, so we'd have negative 2 here. When you divide those, we get 75. So remember, that represents the width. So the width would be 75, and this is all in yards. If you look back at the story problem, it's all in yards. All right, so to find the width, well, we're going to go back over here because we just found that the length is, that the width is 75 yards. So to find the length, rather, we're going to put 75 in here for W. So we'd have 150 minus 75, and when you do that, you get, well, 150 minus 75 is also 75. So the length is 75 yards. So this is actually a square plot of land. So it'll be 75 in length, 75 yards in length, and 75 yards in width. So the maximum area, so like we said, area is length times width. So we would just take 75 times 75. And when you do that, you get 5,625. And this would be in square yards, would be our area. So that's how you do a maximizing area problem. So a little bit simpler than maybe some of the other ones that we've seen. So again, after this, you should be able to do questions numbers. So this is number 5. So after this, you should be able to do numbers 6 and 7 in your homework assignment. So why don't you guys go ahead and work on that. And if you haven't done questions 3 and 4, do that as well.